Here is the surprise about Petawatt and Exawatt lasers. The hardest part is not making the pulse. It is delivering a pulse that survives its own intensity and still behaves predictably on target. As of 2026, petawatt-class ultrashort lasers are already established at multiple facilities worldwide. Exawatt class, by contrast, is still mostly an engineering scaling frontier, not routine user infrastructure. That distinction matters for strategy. A headline peak power number can hide low availability, low repetition rate, and incomplete measurement. In other words, the label can be real, while the capability is not yet industrial. Start with the enabling idea that unlocked the whole field. In 1985, chirped pulse amplification proved you could stretch a short pulse in time, amplify it safely, then compress it back. That one concept broke the damage barrier in gain media and made extreme peak power practical. By 1994, terawatt to petawatt sub-picosecond laser architectures were formalized as a scaling route. From there, the frontier became less about inventing a new principle and more about engineering every weak link. One weak link comes up again and again. The optical compressor, especially diffraction grating compressors, is a recurring bottleneck. You can build enormous amplifier chains, but you still have to compress multi-kilojoule energy without destroying meter-scale optics. Grating damage threshold, coating lifetime, and fabrication precision become the pace setters. If you want a single takeaway for capital allocation, it is this: fund the optics and metrology stack at least as aggressively as the flagship laser itself. Another counterintuitive point is that petawatt describes peak power, not average power. Peak power is energy divided by pulse duration, so you can hit petawatts with a tiny burst. Many systems are single-shot or low hertz and need long recovery and careful alignment. For user productivity, what matters is shots per hour, stable beam quality, and reliable diagnostics. A facility that produces fewer shots with uncertain on-target intensity can be less valuable than a lower peak system that runs all day. That leads to the next major constraint: pulse fidelity in space and time. At these durations, you are pushing from femtoseconds toward attoseconds and approaching the few-cycle, even single-cycle, regime. In that regime, simple approximations break down, and spatiotemporal distortions couple together. A pulse can look perfect in one measurement plane, yet focus poorly or arrive with hidden structure that changes the physics. Losing focal intensity by a factor of 2 is not a rounding error. It can completely change what plasma regime you enter and what particles or radiation you produce. Pulse contrast is just as important, and it is easy to underestimate. If there is a pre-pulse, even a very small one, arriving picoseconds early, it can create pre-plasma on the target. Then the main pulse interacts with a target you did not intend to create. For extreme coupling experiments, the goal is often contrast ratios beyond 10^12 and sometimes 10^14 at picosecond timescales. That is an engineering and diagnostics problem, not just a laser power problem. Now consider what the field is trying to do with these pulses. A major application envelope is laser-plasma interaction in relativistic regimes, including laser-driven ion acceleration. The physics is compelling because it suggests compact particle sources and eventually systems that compete with conventional radio frequency accelerators in specific niches. But the path runs through targetry and reproducibility. To get useful beams, you need structured or solid density targets delivered at high repetition rate with micron-level positioning repeatability. You also need debris management, because target contamination degrades optics over campaigns, and catastrophic damage can end a run instantly. Repetition rate is where petawatt and exawatt ambitions collide with reality. Moving from single-shot to kilohertz-class operation at petawatt peak power is not a linear upgrade. Thermal management, optical damage accumulation, and component replacement cycles become central. At that point, the laser stops being a rare experiment and starts looking like infrastructure. It demands grid-scale energy supply, industrial maintenance practices, and supply chains for large optics and crystals. On architectures, there is an active down-selection question. Should first exawatt systems scale titanium sapphire (CPA), shift to optical parametric amplification like OPCPA, or use hybrids? Parametric approaches are attractive because they preserve bandwidth, supporting ultra-short pulses, but they raise supply chain questions for large aperture nonlinear crystals. Meanwhile, coherent combination of multiple petawatt beams is a promising route around single aperture damage limits. It is plausible, but still hard, because phase control and beam quality must be maintained across many channels.